Hi everyone, my name is Mikayel Egibyan and I work at Wolfram Research for Sound and Vision Group. And today we're going to talk about handwritten text recognition and analysis, what we have achieved and what basically the main motivation was, and we'll figure out what are the actual real life domains that utilize this type of functionality. In the end, I'll just leave some time and we could do Q&A or even after the talk, if there is anything, you could just reach me and we could discuss that. So I'll just stop my video and get on the presentation then. Right, so as I said, we are going to talk about handwritten text recognition and the analysis, and we'll see various techniques, architectures that are used to solve this task. We'll also discuss what kind of domains utilize this problem and what kind of applications are there around and what is the actual situation with the state of the art of the problem in the world and where we stand there. So just to give some background, the actual OCR task, well, is pretty old. It comes from 1870s where people were trying to solve problems, the following problem. So they wanted to transfer the text from one source to another source to allow the blind people to read it. And this was around like 40 years long project, after which Emanuel Goldberg took this further and converted the characters into telegraph code. So in the image, you could see how the actual project looked like, the pipeline. So basically it was the character and the light source coming on the character, and in the background frame, there was the original alphabet. And based on the outcome beam intensity, it was identified which letter corresponds to which input corresponds to which letter from the alphabet. And actually, this pipeline is the main reason why the technology overall was called optical character recognition. And this name is actually carried on to nowadays as well. Later, when the computational power started growing, the technology moved into a new era, so-called image processing era, where people understood how they could analyze the images, how they could process, do some classical operations on images. And this era was pretty long, up to the point it moved to the next stage, which is basically the deep learning, where we have neural networks and all the AI engines to help us to solve the task and to gain actually real high accuracies, which were not really achievable with the classical image processing approaches. Along with the development of the handwritten recognition, another task was growing simultaneously, which was the automatic handwritten text analysis, because non-automatic, I mean by hand, people were doing it for a very long time, maybe for ages. But the start of the automatic analysis varies around like 1980s, where there was already some computational power, not yet enough to solve the task by that time. So they actually had to wait for the AI technologies to come and to help to solve the problem. Nowadays, the digital text appears in a lot of places, and it's so much that we don't already pay attention to it. It's, I mean, literally everywhere, from historical to medical domains, from criminal to mathematical, from the road camera traction to just mobile phone pictures and the signs, car plate recognition. I mean, it's literally everywhere. And just to give you an idea how important it is to handle the exactly handwritten analysis and recognition is the fact that every single day, like millions of petabytes of PDFs, which is like crucially big number, is being scanned and recognized. So this is a real task, this is a real problem that we see in various domains. So when we are talking about handwritten recognition, we envision the following. So we have a text that is written on a paper, for example, here. And then we need the mechanism, we need ways to transfer this into something that computer understands and can print it out in a more common font. So it's easy to understand the following fact that what we have here is a single input image, and we want to have the group of characters, which are like words, lines, blocks, and so on and so forth. So in the other words, if we try to rephrase this statement, is like we have one input and we have a lot of outputs, and each of outputs is a character. So that's why the classical convolutional neural networks are not good fit for this problem, because they are good for classification like problems because of being so-called one-to-one systems. Right, so another problem here is that especially for handwritten text, it's nearly impossible to segment the image accurately and to figure out which part of the text or which part of a letter is contained in which segment. So we need something else here. So basically we need the mechanism to have the handwritten text, to give it to some neural network and to get the already digital output. So one of the approaches to have this working is to go from one-to-one system to one-to-many system, which is, for example, the recurrent neural networks. So what we have here is the understanding of the, so basically we have vector of features, sequence of vectors of features, and we pass this to our neural network, which takes into account the current state, and based on the current state and based on the previous processing output, it basically produces new state and new state and new feature vector. So if basically we try to represent this X here as an input sequence, Y as an output sequence. So if we just unfold this, so what we have here is X's are the sequence of input, sequence of inputs. Ages are our states, and F's are the functions that process both of them and produce new state. So there are various types of RNN, so-called cell architectures. People were at the very beginning very concentrated on vanilla RNN cells, but then they realized that the linearity is actually a trouble here. So that's why LSTMs and GRUs were introduced, and they are in active use even today. Well, not even today. This is the growing technology, actually. There is, of course, a disadvantage in this approach, which is basically the GPU source is not really optimizable for this type of tasks, and which makes the parallelization pretty impossible, and hence making the overall training process very slow. Another approach to try to solve this type of tasks is the usage of transformers, which was actually recently introduced by Facebook. And so one of the main advantages over RNN that transformers have is the training speed and inference. And we're not really going to go into details about transformers during this talk, because whatever solution we have is purely based on RNN plus CNN architecture, and we get pretty good accuracies there. We'll talk about them in a bit later. So, all right, so now that we know that we need one-to-many systems, let's understand analysis. So how the actual architecture would look like, the ideal architecture would look like here. So we said that we need the combination, well, we need RNN because we need one-to-many, but so these, they don't come alone. So a combination of CNN and RNN is used. So in this image, we can see that we have the input image, and we use CNN to extract the features and then pass it to the, and then we need to segment the image into the pixel areas, and which will then be passed to our RNN, and RNN will basically process this sequence, decode, pass it to decoder, and the decoder will eventually give us the result. And actually in the training process, the only difference here is that we need to figure out what kind of loss function we use. For example, here we use we show the loss called CTC, which was introduced by Alex Gray. So basically, these same processed feature vectors are passed to CTC loss, and it's using the ground truth to figure out how to minimize it. Yet another approach to this problem is to use the cross entropy loss. Again, this is moreover like an FYI. We're not going to concentrate on this particular approach because the loss, like with CTC like losses, we can get even better accuracies here. So we'll see. Right, before we dive into the actual loss there, let's talk a bit about the purpose of all of this. So recognizing the handwritten text is one task, but another task is analyzing it. And what means to analyze the text is basically extract features that describe the writing, which will allow us to solve tasks like identification and verification, style analysis, and so on and so forth. So there are a lot of real tasks like in medicine, in pseudosciences, and all around that really need these features to be able to describe what's hidden in the style of the writer. So again, here we have more than one approach, and the first trivial approach that can come to the mind is the use of classification networks, which is basically, we could take a classification network, drop the last layers for the actual classification, and use the feature vector output as our the output as our feature vector. Well, this could theoretically work, but there is a huge disadvantage here. And that is basically, the first thing is whenever you want to retrain this for new samples, you have to do the whole training from the scratch. And this is very computationally expensive. Another disadvantage is that the resulting representation is just a linear combination of class probabilities, which basically is a really big problem if the number of classes is big. I mean, for small number of classes, this can be a suitable solution, but not for this type of task where we have like a very big number of classes. Another approach, which is more applicable here, is so-called deep metric learning. So what is the point of that? So we have the loss, and it basically, it knows the classes of the images we have, and it forces the representations of these classes to be far from each other or close to each other based on the similarities and in Euclidean space. So aside from many advantages over the classical approach, this approach gives us ability to use the nearest neighbor classifier on top of the representation, which is actually a very important problem to solve the scaling problem. Of course, as everything in this world, even this approach has some disadvantages. And besides being slow, there is a good chance for divergence. A very, well, mostly known example of deep metric learning approach is so-called triplet loss approach. So now, knowing some background about what methodologies, what architectures are there, let's talk about maybe one of the most important things in this task, which is the loss function definition, because this is something that is going to make your network have higher accuracies. One of the things. So again, let's imagine we have writings from different people. So like this is taken from so-called IM dataset, and we have writings from various people. So they write various texts and so on. So we need a good loss function to help us to extract features in a way so that we could do both identification and verification at the same time. So as a first attempt, we took just the classification network, and the reason just was we needed some, like ground to start training the deep metric learning approach, not to do everything from scratch, to have some ground as a pre-trained model. And of course, since the classification network has its disadvantages, we went with, the first attempt was the most popular triplet loss based training. But unfortunately, as you can see in the snippet below, due to the large intra-class variability of the data, we got divergence. And at this point, we had to rethink and figure out what we can do to fix the problem, because the classical, well-known approach didn't seem to work here. So, and that made us to use some new loss function, which we call as Bhattacharya loss layer, Bhattacharya loss function. So the reason it's called Bhattacharya is basically it uses the distance formula for Gaussian distributions that Bhattacharya introduced, and that's why the loss is also named after him. So the point of this loss is basically to, instead of, is to take into account, it's to calculate the intra-class and inter-class distances of Gaussian histograms and stimulate these Gaussians to be as far as possible. So basically, the further they are, the less the intersection is, the better it is. Like, for example, in the snippet below, you could see that here we have like approximately the overlap is about 6%, which is pretty good to use this as a feature extractor for the further development. So once again, so the loss function definition is one of the most important parts here. All right, so having some theory, let's see how this thing comes to life. So just to show a very toy example that everyone can reproduce, let's just pick some fonts for system fonts that I have on my machine. They are more or less similar to Handwritings. We'll just use that font to generate some images, label them, and everything will look like this. So we will have the image and we will have the ground truth for that. So we have this small data set here. We can just now split between trained data and test data. And we'll just use simple utilities to create basically the architecture with the laws and all the stuff that we just talked about. And so basically we can see we have the input. As we saw, it passes to CNN, retrieves the features, and then it passes to RNN, the sequence, which basically then will pass it to the decoder and give the output to us. So we could just train this model right out from there. I'm training on CPU just because I don't have GPU on my machine. Even with CPU, this training lasts about 5 minutes for me. We are definitely not going to wait there. So I'll just stop this and I will use the result that I have prepared before. So it's like 4.5 minutes on my CPU. And we can go ahead and jump into testing it. So basically, we can see that the result is pretty reasonable, pretty impressive. Well, in this particular case, this is actually perfect, but we might have some, for example, like deluxe, it's like Telalu or whatever, but take into account that the data was very, very small, and even with the low data set, we can get very reasonable results. So just a toy example for you to understand. But now if we want to see how this would behave with a bigger data set, with a proper training, let's see what we have here. So let's just take this snippet. This will be the image we will be playing with. So first of all, we need to find basically where the text is located in the line. So we use find image text, which is actually not designed for this type of purpose, though it seems to be doing a reasonable job here. We might actually use some lexicons, language models, to improve the output result. So very, very straightforward small function, which will basically take the image, run it through the network, give the output, apply the lexicon model and the language model if there is some, and we can just jump and test it. So we can see, I'll just rerun this. All right, so yeah, there was some initialization thing. So we can see that on my CPU, like for that image, 0.7 seconds, not bad. And we have the actually word by word recognition happening here. We could also apply the lexicon, which is very trivial lexicon that I used. We see that the time jumps up a bit, but now we get some alternatives to the recognition. And we could go even further and take any language model to improve the recognition based on this suggestion from lexicon model or whatever. So if we look what is going on in the word, on this topic, so if we take all possible architectures around, we'll see that we are standing right now at some like 5th place or whatever. We can see that like from 2nd to 5th place, the cluster is very small. And if we go and pick the CNN plus RNN architectures only, we are again at like 4th place. So one of the leaders here is not using CNN plus RNN. And again, the 2nd to 4th place is a small cluster here. And just to see, so another sample that produced like visually gives the idea what these numbers, these accuracies, these error rates means. So this is a text that I'm having trouble to read some parts of it, but we get pretty reasonable results on there. And the good thing is that we have very strong vision how we can improve this and go up to, I don't know, like our vision is to go up to 2% error rate or around or whatever. But I mean, we have the distinct steps. We know how to improve things. So that was on the recognition part. Now on the analysis part, let's face this kind of problem, which is also known as forensic analysis. So we'll just take writings from 3 people. So whatever I'm taking here, writings from Stephen Wolfram, Albert Einstein, and Marie Curie. So these are the writings. And now we're just going to try to do something with this. So before we try to, so as I said, so this ResNet style is the network that we trained and created. So this is basically going to extract feature vector from the input image. And with that feature vector, we are going then to be able to analyze. This looks something like this. So you have the image, and then from this image, based on the handwriting, you have a vector of numbers, which is basically the descriptors for your for the handwriting. So again, like a few small utilities. For example, we need the utility to patch the image into pieces, and then we will try to solve the problem here. So this is again very simple function, and we will see. For example, we are trying to see if the 3rd image, which is this from Stephen Wolfram, is the same with the 3rd image from Albert Einstein here, and we get false here, which is actually what is expected. And then we can do the same thing with 2 writings from Stephen Wolfram, and we will see that they actually match. Though pay attention that the text is pretty random. It's not really written in the same way. It's not taken from the same snippet or so. So just to have an overall, just a bit bigger overview here, we can see that, in fact, the results are very reasonable, even with the tiny data set that we taken. So we have very small data set, but even with that here, like true means basically we correctly said that these 2 writings are the same, and here true means that we correctly said that they are not the same. So we can see that we have only a few failures here. And again, the data set is very tiny, but we can take this tiny data set even further now. We can take, like only 3 snippets from each of the people we had here, and we can just, like create some test data there, and we'll just take 3 from here, and the rest we'll just take for testing. And we can run a very simple classifier, which is pretty fast here. And right, so we can see that with this tiny data set, we already got around like what, 77, okay. Yeah, last round it was 80, whatever. So yeah, but you can see that there is some epsilon here. So, and this is pretty good. We can actually see that interesting fact. For example, Maria Curie and Albert Einstein there is a big number of failures here. And if you go and dig into the problem, you will see that actually Maria Curie's and Albert Einstein's handwritings are very similar to each other. And that was something interesting we figured out when preparing this example. So, and the final, as a kind of a final conclusion to this example, so you could do the following. You could basically put in the writing and get the identification of the writer. So this is basically just a combined example for both for the verification and identification. Last but not least, let's talk about a bit different domain of the usage of the technology. So this is basically about the signature validation, verification, and identification. So we have random snippets of signatures, and we'll just divide this into, again, training and testing. Pretty straightforward here. So let's look at the keys to understand. So we have like numbers like 001, and then we have 001 underscore forge. So basically these 001 like numbers represent people who put their signatures there. And number underscore forge means basically someone tries to fake this signature. And now we're going to try to see if we could identify who is the writer for the signature, and if we could distinguish, basically verify if the signature is valid or invalid. So again, we'll just put our training data into the classifier. Again, pretty fast, taking into account I don't have any GPU here. And what we get here, okay, so we get like 93%, which is reasonable. Well, the data set is not that small here, but whatever. So this will give us to the solution to the identification problem. So we will basically put an image, and then it will tell who is the original author, basically, of the writing with 93% of accuracy. Now, when we have this part, we can go further and try to adopt this to the verification part, which is basically, for example, let's see here. So we have the following structure here. So we have pairs of signatures. Some pairs contain writings from the same person, basically, which is not forged. And some contain one original and one forged signature. So we are again going to split this between train data and test data and see how our classifier behaves here. So there is some minor warm-up required because the classifier needs to pre-process the output, and whenever it thinks it's ready, it will give us the result there. Right, so yeah, we have like pretty big data set here. So all right, okay, so it's going and it's done. All right, so let's see what we have here. Okay, all right. Okay, so we have 96.5 accuracy. This is number of the test examples it was run. And let's just see this in action. So basically we give it a pair, and it basically says if both of them are valid. Like, for example, the first one is the second one, the forge of the second one, or this is actually from the original writer. And this is the counterexample here when you have the original writing and then you have the forge, and it says, yes, this is a forge. And so, as I said, we have what, 96.5 here. So the state of the art of the problem from 2017 was 4.63. And we have 3.5 already with this network, which is yet to come with a lot of more improvements there, as I said before. So that was actually all I had prepared for today. I'm happy to take some questions. I know we went just a bit over time, sorry for that, but I'm happy to take any questions now or even afterwards if there are any. All right, I don't think anything here, and if there is no anything else in this Zoom chat as well, then I'm just taking this as no answers. So thank you for your attendance. I'm happy even to take questions after the presentation. Just feel free to reach me out and ask anything you want to. Thank you.